Hey guys, welcome to DataTrek, your one-stop channel for all the data science and machine learning updates. In today's video, we will be looking at principal component analysis, which is a dimensionality reduction technique. So what is this problem of multicollinearity? Why is it's a problem in machine learning, and how techniques of dimensionality reduction like PCA helps in overcoming it? We'll look into more details, and as well as we will have a practical example. So visually it's clear that what PCA is doing through codes. So with that, let's get started. Suppose we are solving a machine learning problem to predict house prices, and we have taken three different features. One is size of the house in square feet, number of bedrooms and number of bathrooms. At first glance it seems good, and all the predictors, which is the size of the house, number of bedrooms and number of bathrooms, seems good independent predictors. However, there is a hidden issue. The size of the house is often closely related to the number of bedrooms as well as number of bathrooms. More the number of bedrooms, more the number of bathrooms, definitely the size of the house will also be bigger. For example, 3000 square feet house has 4 bedrooms 3 bathrooms, and 2000 square feet house has 3 bedrooms 2 bathrooms. So for predicting this house prediction problem, we have used 3 variables, and there is a hidden issue that all 3 variables are actually very similar and kind of related to each other. So this is the problem of multicollinearity, where the predictors are actually collinear and very much similar to each other. Now, why this is a problem? The machine learning model may still predict accurately, but the explainability will go for a toss. What it means is that it will become difficult to determine which variable truly contributes to the price of the house. Because there is this multicollinearity, it will be very hard for model to explain it. Secondly, there is a chance of overfitting, because since the features are redundant, kind of, they are carrying the same information, the model may try to overfit. And the third problem is reduced statistical significance. Normally what happens, we do the statistical significance, the p-value estimation of the feature, to understand whether that feature is really important to determine the target variable or not. Because all the features are redundant or carrying the same information, it will become very hard for the model to figure out whether which feature is statistically significant or not. So these are some of the problems: explainability, overfitting, and reduced statistical significance. Now there are other ways also to solve this problem of dimensionality. Multicollinearity, but one very popular way is using dimensionality reduction techniques like PCA, which is principal component analysis. To understand PCA, we need to understand a bit of mathematics. The mathematics, let's start with vector projection. Suppose we have a vector which is OA, and we want to project it into OB. So what is vector projection? It is the 90-degree shadow that we drop of that vector to the another vector where we want to project it. And from the theorem of trigonometry, we know that the length of the projected vector will be OL, which is A cos theta. If the length or magnitude of vector OA is A, then the length or magnitude of the projected vector will be A cos theta. Now A cos theta can be given as A dot B divided by the magnitude of B. Why? Because A dot B is A magnitude, B magnitude cos theta, and B magnitude will get cancelled out. You will get A cos theta only. So projection of vector A on vector B is given by A dot B divided by the B's magnitude. And similarly, the vector projection of B on vector A, suppose we have to project this on this, what we will do? We will extend it and draw a 90-degree shadow of this vector on OA vector, and the length of that projection of vector B on A will be A dot B divided by A's magnitude. So this is the formula for vector projection, and the idea of vector projection is no matter which vector you have, you can always project it into another vector, and what will be the length of the projected vector or what will be the magnitude of projected vector, we can find through these formulas. Let's do an example. Suppose we want to project the vector 4i 2j plus k onto another vector 5i minus 3j plus 3k. Then the projection of first vector on second vector will be the dot product of these two vectors, which is 17, 4 into 5 plus 2 into minus 3 plus 1 into 3 divided by the magnitude of the second vector on which we are projecting, right? So that is the magnitude of this vector, 5 square minus 3 whole square plus 3 whole square and square root of it. So this will become 17 upon root 43. So this is how you calculate the magnitude of vector A when you project it on vector B. You do A dot B divided by B's magnitude when you are projecting A on B, and vice versa when you are projecting B on A. And always the vector projection is 90-degree shadow of the vector that you want to project on the another vector. So vector projection is clear. Now why this vector projection was needed to understand dimensionality reduction or PCA, we will see in the next slide. Suppose we have two-dimensional data point, which is, you can think of it as, you have a ML model where you have two predictors, x1 and x2. So you have two-dimensional data point. Each data point can be represented in 2 dimensions, and all these yellow points you can think as your data points or samples. Or you can, in this case, let's say you are using the size of the house and number of bedrooms as the two predictors. They can be x1, x2, and all the different houses can be one of the points. Now what we want to do is, we want to reduce the dimensions from 2 to 1 dimension, because we feel that if we use two variables, they are collinear to each other, and there is a problem of overfitting. The model explainability may go for a toss, statistical significance may be a problem. So we want to reduce dimension to 1 from 2. So what we can do is, we can take any vector, and project all these points to that vector, and the magnitude of all the points or all the vectors when falling in this vector will become the new dimension, and the dimension will reduce to 1, because we are projecting each and every point to one of the vectors and taking the magnitude as the new value for each data point. Now which vector to take? There can be multiple vectors. For example, let's take the example of this red vector and green vector. If we project all the points to all the yellow points to red vector, we will have very high variance, while if we project all the points to green vector, the variance will be low. Why? Because you can take the example of all the blue points. If I project these blue points on red line, this point will fall here, 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 and this point will fall here. So we are capturing good amount of variance. While if we project on the green vector, you can see that this blue vector will project it here, and this blue vector both will fall on the same point, this one, right? So you can see that only in very small amount, like let's say from here to here, you will be able to project everything, while for the red one, the points will fall from here till here, right? Because you will do a perpendicular shadow drop. And you can see in the second plot as well, the variance is very high, because you are capturing larger area, or that's why the variance is very high for the red vector, while variance is very low for the green line, because all the points will mostly get distributed just in this area, right? So that's why the variance of green vector is low, while the variance of red vector is high. So this is how we can project two-dimensional vector, by projecting them into one of the vectors, and we can take magnitude as the new value. And ideal thing to do will be take a vector where the variance is highest, because there is where we can have maximum information, right? Because when we have higher variance, it means that different points are capturing different information. But if multiple points are falling on the same point, or they are just in a small area, it means there is very less information we are able to capture. While if we are able to capture more information, more variance, then that is better. So that is the idea of principal component analysis. And we want to find dimensions along which we should project our data points, so that the variance covered is highest, the information gain is highest. And also, suppose if we project the data to this vector, next time we will project to a vector which is orthogonal to it. So there is no collinearity in the two vectors, right? So we will make sure that all the vectors in which we are projecting are orthogonal to each other. And how many vectors we will need? We will need as many vectors where we feel that information gain is significant till the cutoff. Let's say only two vectors are capturing most of the variance, then only 2 dimensions are enough. But if let's say 10 dimensions are needed to capture the variance, then 10 dimensions are needed. So we will figure out that how many dimensions are needed, but the idea is that we project all the data points to some of the vectors, and make sure that all the vectors in which we are projecting are orthogonal to each other. So how to find this vector? So for that, we know one important property, that we want to maximize the variance. So let's use that to derive that what should be those vectors in which we should project our data points. We have n data points, capital N data points, and each data point is of d dimension. Now the goal is to find a vector where we can maximize the variance, right? Next is we want to find the vector in which we should project, so we are able to capture the maximum variance. So let's assume there is some vector u in which we project, then the magnitude or the new value after projection will be u dot x, right? We have already seen the projection formula, and this will be the magnitude, and since the direction will be of vector u, it will be, we can multiply by u1. And also we are ensuring that u is a unit vector, so it doesn't happen that we are just increasing the magnitude of u to say that we are capturing more and more variance. We are fixing that the vector is unit vector, so u is a unit vector, and if we project all the data point to vector u, it will become u dot x, and the direction is of u1, that's why we are multiplying one more u1. Now this is the projection of one data point. We need to do it for all the data points, and what will be the mean? It will be the mean of all those projections, right? Since u is a unit vector, the mean of all the projected data points will be controlled by the x vector only. So the mean can be given by u dot x bar multiplied by u, which is the direction of u vector, but the mean will become x bar, right? Because an x is nothing but mean across all the data points. So we know projection is this of each individual point, and the mean of all the projected data points will be u dot x bar u. Now what we want to do is we want to find the unit vector which can maximize the variance, and formula of variance is each data point minus its mean whole square across all the data point. When we calculate that point, it becomes the variance. So variance is nothing but how each data point is differing from the mean. We take a square of it and we do an averaging across all data points. So this is the formula for variance. Now in vector form, it can be written as, we can take the u outside, it will become xn minus x bar whole square. Now in vector form, we can again write it as xn minus x bar, xn minus x transpose, and we can also write the u square as u transpose u, because in vector notation we can write it this way, right? X square becomes x transpose x. Similarly here xn minus x bar whole square will become xn minus x bar transpose. Now you can see something very interesting. What is this? This is nothing but this is the formula of covariance matrix, right? So what is covariance matrix? That if we take, since we said the vector is of d dimension, we know how much the two dimensions are varying with respect to each other. We can find easily using the covariance matrix, and this is the formula for covariance matrix. So we wanted to maximize the variance of the projections, and it came out that this becomes u transpose su, where s is the covariance matrix, and we know we want to maximize this term, and also we have initially assumed that u is a unit vector. So we want to maximize this term with subject to the constraint that u is a unit vector. U is a unit vector, so the magnitude of u is 1, and u square in vector notation can be written as u transpose u. Now whenever we want to solve such kind of problem where we want to maximize something and constrained on something, we can use Lagrange multiplier method. So we will maximize u transpose su plus lambda 1 minus u transpose u. So this will become like the constraint will go this side, 1 minus u transpose u, and one lambda will come up, which is called Lagrange multiplier. So this is how we solve constraint optimization problem. Now we want to find the u vector, right? To find the u vector which is unknown, we can take a derivative with respect to u and equate it to 0, so we can find the u which can maximize the variance. So if we do that, this term, there are two u's, so one u will only remain, 2s u1 it will become, and here this term 1 will become 0, and this term will become again 2u lambda, because the x square's derivative is 2x, right? So that's what happening. Now we can take the we can move this portion on the other side, and this is what we get. Now this is very interesting. We are saying that we want to find a vector u such that where we project the variance is maximum, and one more thing is happening here. We are saying that when we multiply this vector with our covariance matrix, it is getting scaled by lambda. Now if we go back to mathematics, we know that whenever a vector gets multiplied by a matrix, what happens? It can change direction, or it can get rotated, it can change magnitude differently in different dimensions and so on. But here it's not getting rotated, it's not changing direction, it is just getting scaled. So what is this? This is the property of eigenvector of a matrix. Whenever we multiply a vector with a matrix, and if that vector is just getting scaled, it's called the eigenvector of that matrix. So we can say that u is nothing but u is the eigenvector of that covariance matrix, right? So this is what we can see. This shows that u1 is the eigenvector of S with eigenvalue of lambda. The eigenvalue corresponds to the variance along that direction. So what principal component analysis is? The first principal component is nothing but the eigenvector corresponding to the largest eigenvalue of covariance matrix. Second eigenvector will become the second dimension in which we can project. Third eigenvector will become the third dimension, and how much variance is captured we can see depending on the lambdas, lambda 1, lambda 2, lambda 3. As the lambda becomes very small value, we can say that there is not enough variance left in the new dimension, right? So that's the mathematics of PCA. When we will see the practical example, it will become visually very clear. Just revising what we just learned, that in machine learning there are cases when two or more features are very much correlated, and they can lead to the problem of explainability, overfitting, reduced statistical significance and so on. And one technique to reduce dimension is PCA, where we find a vector dimension where we can project the data points such that the variance captured is maximum, and we can do that for another dimension also, and the another dimension for which we are doing will be orthogonal with the first dimension, and so on, so that there is no correlation left in the dimensions in which we are projecting. And it comes out when we are trying to find that vector which maximizes the variance is nothing but the eigenvector of the covariance matrix, with the first vector having the highest eigenvalue will be the first principal component, and so on. And as the eigenvalue becomes very small, we can say that there is not much variance left to be captured, and those many dimensions are enough. Suppose we started with 100 dimensions, just in 5 dimensions if we are able to capture most of the variance, we can say that this 100 original dimension can be projected to just 5 new dimensions, and our data points will which was initially n cross 100 will just become n cross 5, right? And in this n cross 5 there is no problem of multicollinearity, and any model that we fit on it will be free from the curse of dimensionality or problem of multicollinearity and so on. But there is one problem as well. The new projected dimension are not that explainable as the original dimension. Originally you knew that what was the house feature, which was the bedroom feature, which was the kitchen features, and so on. In the new dimensions you can't say that what that new dimension is. It's a latent feature. Now let's look at the practical example, and things will become super clear. I will attach the link of this notebook in the description section. So what I have done is, let's look at a dataset which I have created to explain visually how PCA works. I have created 2 datasets. The first dataset is created in such a way that there are 100 data points and there are 10 features. All features are randomly drawn from normal distribution with distinct mean and distinct standard deviation. Each feature is drawn from a normal distribution with varying mean and standard deviation. While the second dataset has 3 features which are randomly drawn from normal distribution. It also has totally 10 features, but the first 3 features are randomly drawn with varying mean and standard deviation, and remaining 4, 5, 6, 7, 8, 9, 10, which is remaining 7 features, are just linear combination of first 3 features. So repeating, the first dataset has 10 features, all are randomly drawn, all are carrying distinct information, new information, while in dataset 2 only 3 features are carrying the distinct information, and other features are just linear combination of the first 3 features in some way, like 1.2 into this plus 0.5 into this. I have plus, I have minus, I have multiplication, I have divide, all these linear combinations of the first 3 features to derive the next 7. Now let's do an EDA. This is how the dataset looks like. This is dataset 1, this is dataset 2. Next, what we can do, we have implemented PCA to project the data points to the new dimensions which are orthogonal to each other, and these new dimensions are nothing but the eigenvectors of the covariance matrix. So what it is telling is that in the dataset 1 all 10 dimensions are needed to explain the variance, while in the new dataset just 3 new dimensions are enough to capture most of the variance. And you can see the new dimensions which are PC1 to PC10 here, and also PC1 to PC10 in the second dataset. Only 3 are enough. You can see that remaining ones are all zeros. There is no variance, no information left to be captured in remaining of the principal components. Let's also look at the covariance matrix. The first dataset is already less correlated. You can see that the diagonal values, which is feature, is correlated with itself but not with other features, because we have drawn all the 10 features independently of each other, so they are very less correlated. And in the new dimensions the correlation is almost 0, because in the new dimensions we know the PCA works as the new dimension is the eigenvector of the covariance matrix, and each one are orthogonal to each other, so there is 0 variance in the new dimensions. Here is still some very less amount of variance you will find, but in the new dimensions there is no covariance. Let's look at dataset 2. In dataset 2 there was already very high covariance or correlation, right? Because the remaining 7 features were derived from the first 3 features, so there was already very large correlation. You can see many red and orange points showing that high correlation. And in the new dimension there are just 3 new dimensions are needed to explain all the variance, and among them there is 0 correlation. The feature is correlated with the itself but not with anything else. So that's it. We can see that all new projected dimensions are orthogonal to each other. So this is how PCA works. So that's it in this video, where we looked at principal component analysis. In statistics and machine learning, PCA involves finding the eigenvectors and eigenvalue of covariance matrix and projecting all the data points to these eigenvectors of the covariance matrix. The eigenvectors represent the principal components and the eigenvalues indicate the variance. PCA is widely used for dimensionality reduction and data compression by projecting data points onto an eigenvector associated with the highest variance as determined by their corresponding eigenvalues. So with that, we come to the end of this video. Please like and subscribe and stay tuned for more such updates. Bye.